In the previous lessons, we learned how to use the periodic table to determine the number of protons and the number of electrons for each atom. Now, in this lesson, we are going to look at isotopes. Well, what is isotopes? Isotopes are particular types of atoms of the same elements. Well, we know that based on the periodic table, each element, okay, like carbon right here, is identified by its unique number of proton, which is the atomic number there. So each element is defined by the atomic number or the number of proton on the periodic table. But if we look at the average atomic mass of an element, there's a reason why we use the term average atomic mass. That is because there are different atoms of the same element. How is that possible? Well, each type of atom actually have different number of neutrons. So the number of neutrons are not the same for all the atoms of the same element. Some atoms of the same elements have less or more neutron. And if that is the case, you would have your different mass number. And we know that mass number is the number of proton plus the number of neutron. And for that reason, each element on the periodic table have this average atomic mass rather than just using the mass number, because different isotopes will have a unique mass number. But here's another thing. The percent of abundances for different isotopes of the same element are not the same. If we look at carbon, for example, here I have the isotopes of carbon, carbon 12, carbon 13, and there are other isotopes of carbon as well. And we look at the average atomic mass, which is 12.01, right? This is very close to 12. Well, what does that tell you? Well, it turned out that 98.93% of carbon is carbon 12. And that makes a lot of sense because the average atomic mass is very close to the mass number of carbon 12. And only 1.07% of carbon isotopes is carbon 13. And notice how 12.01 is far away from 13. So consequently, the average atomic mass of carbon is going to be 12.01, which is a lot closer to 12. Now in this lesson, we are going to look at how to write an expression to represent an isotopes of an element. Well, there are two ways to express or write an isotope. First, we have an element followed by the mass number, just like we have carbon, or C13, or oxygen, or O16. Then we have this more complicated one, where we have the symbol of the element, we have the net charge, we have the mass number, and notice how we have the atomic number. And this atomic number is also equal to the number of proton. And look at this mass number right here is always larger. So larger on top. That way we can just subtract directly to get our number of neutron. So let's do an example problem. Here we have this generic format. We have 8 carbon, 8 neutron, and 10 electron. Well, what is 8 plus 8? Well, 8 plus 8 is equal to 16. So there you go, that's your mass number. And this 8 right here is just your number of proton, that's all it is. But here we have the net charge. Well, to find the net charge, you take the proton minus the number of electron. 8 minus 10, what is that going to tell you? 8 proton minus 10 electron. Well, what's 8 minus 10? We have 2 minus. Okay, and remember when we write the charges, the negative is after. Or the charges is after. So we have 2 minus right here. If you put the charge in front of the number, that represents oxidation number instead of charges. Now let's try another problem. Here we have 29, and then we have F minus. Well, again, we know this is your mass number, okay? And you subtract that, what do we get? 20 minus 9, that's 11 neutron. First of all, the number of proton is the same thing as that number, 9. The number of neutron, we just did that. 20 minus 9, the larger number minus the smallest number, we have 11. And the number of electrons, well, what is -1? Well, if this were to be equal to 1 minus, that means it has gained 1 electron. So gaining from what number? Well, originally it has 9. So we have 9 plus 1 equal to 10 electrons. Let's try another one where we have the positive charges. Well, the number of proton, again, this is just the same thing as the atomic number, 13. Neutron, we have the top number minus the bottom number, which is smaller, turn out to be 14, okay? And what does that 3 tell you? Well, it has lost 3 electrons. Well, what number is it losing from? In this case, it's always, again, proton equal to electron when we have a neutral net charge of 0. In this case, 13 minus 3 equal to 10. Now let's try another one with a negative charges. Again, this is the number of proton. And then the number of neutron, you take the top number minus the bottom number, will give us 8. So we have 8 neutron. And for electron, this tells you it has gained 3 electrons, okay? So we have 7 plus 3 give us 10. And that 7 is coming from there, okay? Here's the last one. We have another isotopes of hydrogen. Well, the number of proton is just going to be that one. The number of neutron, 3 minus 1 equal to 2. So we have 2, and that tells you has 1 minus. So in this case, it's going to gain 1 electron. So what do we have? Well, 1 plus 1 give you 2. And that is how you interpret isotopes to determine the number of proton, neutron, and electron.